For this online activity, we will be investigating how to determine the rates of motion for different tectonic plates. First, we will make estimates of the rate of spreading from mid-ocean ridges, also known as spreading centers. In Part 2, we will estimate the motion of the Pacific Plate based upon our measurements of the distances between Hawaiian Islands and the Hawaiian Island chain and seamounts and the Emperor Seamount chain. Print out a copy of the online activity so that you can fill this out and turn it in at our next class when it is due. I will not accept late assignments. We will spend a little time discussing this activity. Watch the short review video about plate tectonics. This video comes from Ida Awad and can be found on her YouTube channel listed below. Her video refers to parts of her class, but we can use the video to review some of the science behind plate tectonic theory. Here is a map of the Earth. Major plate boundaries are located as red, green, and magenta lines. Topography and bathymetry are represented by color. Low elevation is green, and high elevation is brown. Deep water is darker blue than shallow water, which is lighter blue. There's a graticule grid showing the degrees of latitude and longitude with labels in the margins. Note how the equator is marked as 0 degrees, as is the prime meridian, which runs through Greenwich, England. Two plate boundaries we will use to investigate plate motion rates are the Mid-Atlantic Ridge and the East Pacific Rise. Both are mid-ocean ridges, also known as spreading centers. Later in this online activity, we will take a look at the motion of the Pacific Plate based on our observations along the Hawaii Island chain and the Emperor Seamount chain. First, we will review something about the Earth, the latitude and longitude coordinate system, and maps. The map on the top center looks like the map we are using in our online activity. The latitude and longitude graticule grid lines are rectangular. This is because these maps are using a projection to place the three-dimensional Earth onto a two-dimensional map. These two versions at the bottom are also projections of the Earth, but they show how the longitudinal lines, meridians like the prime meridian, actually converge, come together at the poles, as does the view of the globe in the upper right-hand corner. This is a projection that even more demonstrates how these longitude lines, the meridian lines, converge at the poles. This figure shows again how the meridians converge at the poles. This also shows how the latitude lines remain parallel throughout the Earth. Why does this matter to us for our online activity? The degrees of latitude are the same distance from each other throughout Earth, while the distance between meridians is at a maximum at the equator and diminishes to 0 at the poles. We are making measurements between meridians, but we will restrict these measurements to the equator. This is the only place on Earth where we can convert degrees of longitude to nautical miles with conversion factor 1 degree equals 60 nautical miles. We can always convert degrees of latitude to nautical miles using this conversion, but because the lines of latitude are parallel to each other, so are at the same distance from each other throughout the entire Earth. Suppose we want to know the distance from the Great Lakes to Miami, Florida. How could we determine this? Yes, we could use a ruler to measure this distance on the map. We will make some measurements on this map together. The map that you printed out for this example may be slightly different than the one we use in this presentation, but it should be close. If you do your own work, I will be able to tell. Your measurements should be slightly different than the ones I make in this presentation. We will use this map as a basis for calculating our plate motion rates. Here, we place a ruler on the map and we'll use the metric units on the ruler. The units here are labeled in centimeters, but let's use millimeters. There are 10 millimeters in a centimeter. How many millimeters are there from the Great Lakes to Miami, Florida? Yes, there are about 21 millimeters between the Great Lakes and Miami, Florida. Is this the real distance between these two locations? No, it is really much further between these two locations. As a side note, we also know that there are 1,000,000 millimeters in a kilometer and 1,000,000 years in 1,000,000 years. So later it will be simple to convert from kilometers per million years to millimeters per year. More on this later. Suffice it to say, let's use millimeters. How many millimeters does our ruler say? How do we determine the real-world distance between these two locations, or any locations on this map? We need to determine the scale of the map and formulate a map distance to real-world distance ratio conversion factor. These gradicules show us a real-world distance on the map, and we can use these to determine the scale of the map. Or, for every millimeter that we measure on the map, how many millimeters that would be in the real world. This arrow shows a distance of 10 degrees in latitude. Note that 1 degree in latitude is 60 nautical miles. How many nautical miles would 10 degrees in latitude be? Yes, 600 nautical miles. How many millimeters are there between 0 degrees and 10 degrees south? 11 millimeters. Is this the real world distance? No. Let's do the calculation to figure this out. How to convert map distance into real world distance. Here are our two measures. The map distance is on the left and the real world distance is on the right. From this, we find that there are two possible conversion factors. 11 millimeters per 10 degrees or 10 degrees per 11 millimeters. If we want to convert units, we want to use a conversion factor that lets us cancel the units. If we want to convert 11 millimeters to some distance with the units in degrees, do we use the ratio on the right or the left? Yes, we want to use the conversion factor ratio on the right. Since this ratio has millimeters in the denominator, the millimeters units cancel and we are left with the degrees in the numerator. Let's see the math and apply this. Step 1, write your equation. Step 2, cancel the units. Step 3, perform the arithmetic like we did in elementary school. Step 4, check the answer to see if it makes sense. Yes, we have confirmed that 11 millimeters in map distance is equal to 10 degrees in the real world distance. Let's do a real example now that we have a conversion factor ratio for this map. We will use this conversion factor for all the measurements we will make during this online activity using this map. Suppose we are interested in measuring the distance demarcated by the orange arrow on this map. What is the first step? Yes, place a ruler on the map and make a measurement of the map distance. In this case, I get 24.5 millimeters. What do you get? Follow along with my measurement and then do it again with your measurement. The calculation you make with your measurement should be very close to my calculation. Here are the steps. Write your equation, 23.5 millimeters times the conversion factor, 10 degrees to 11 millimeters. Step 2, cancel the units. There are millimeters in the numerator and millimeters in the denominator. Cancel them out. Then step 3, perform the arithmetic like we did in elementary school. 23.5 times 10 is 235. 235 degrees divided by 11 is 21.4 degrees. Step 4, check the answer to make sure it makes sense. If we take a look at the map and the arrow, we can see that the arrow spans a little more than two 10-degree grid lines. This makes sense since our calculation is 21.4 degrees. Step 5, our next step will be to convert this real-world measurement in degrees and convert it to kilometers. But first, make the calculation with the measurement that you made with your map. Not everyone will have the same measurement, so your answers will be slightly different, though some may turn out to be the same. Step 1, write your equation. Step 2, use your conversion factors to change the units from degrees to kilometers. We have 21.4 degrees. We multiply that by our conversion factor, 60 nautical miles to 1 degree. Then we cancel the units of degrees and multiply out. 21.4 times 60 is 1,284 nautical miles. Then we multiply the nautical miles by our conversion factor, 1.852 kilometers to 1 nautical mile. We cancel the units of nautical miles and multiply it out to conclude with 2,378 kilometers. The length of that arrow is 2,378 kilometers. Finally, think if this answer makes sense. Do a little math in your head as a check. Round up or down the conversion factors and then do some multiplying. For example, round the measurement to 20 degrees and use a conversion of 2 kilometers for each nautical mile instead of 1.852. What do you get? I get 20 times 60 times 2 is 2,400 kilometers. This is pretty close to 2378, the answer we got when using the correct conversion factors. It is always good to do a little checking of your math. We almost have enough information to calculate a plate motion rate. Recall that a plate motion rate of velocity is defined by a distance divided by a time. Rate equals distance divided by time. We have a distance, We just needed time. How old is the oceanic crust at the East Pacific Rise? Yes, the oceanic crust is new at the East Pacific Rise, so it is 0 millions of years old. 0 MA. How old is the crust at the edge of South America? That was a trick question. I've not told you yet, though you could look it up. Along the equator, the oceanic crust at the edge of South America is about 20 million years old. 20 MA. So, step 1, write your equation. Rate is distance over time. Step 2, insert the variables and solve for rate, the unknown. Rate equals 2378 kilometers, your distance, divided by 20 MA, your time. Dividing that out, we find that our rate is 119 kilometers per million years. Step 3, convert the rate from kilometers per million years to millimeters per year with your conversion factors. Note that there are a million millimeters per kilometer, and there are a million years in a million years. Step 4, cancel the units and other numbers. We can cancel kilometers, we can cancel MA, and we can cancel a million in the numerator and a million in the denominator. And if we multiply this out, we find our rate to be 119 millimeters per year. Do you see something similar between the rate of kilometers per millions of years and millimeters per year? Yes, since the number is the same, since there are 1 million millimeters in a kilometer and 1 million years in a million years, the number does not change. Here is the measurement you need to make for your mid-Atlantic ridge spreading rate calculation. Show all of your work. Recall from our last activity that this is the Geological Society of America geologic time scale. I provided a link to the file on the website and in this digital presentation. We will use this time scale to determine the ages to use in our plate motion rate calculations. The age of the oceanic crust just offshore of Africa is mid-Cretaceous in age. Use this time scale to estimate what mid-Cretaceous is. Use a value that is midway between the beginning and ending of the Cretaceous period. Note the years in millions of years are on the right of this figure. The Cretaceous period begins at 145 million years ago and ends at about 66 million years ago. And here is the measurement you need to make for the East Pacific Rise spreading rate calculation. Show all of your work. The age of the oceanic crust in the Western Pacific is mid-Jurassic in age. Use this time scale to estimate what mid-Jurassic is. Use a value that is midway between the beginning and ending of the Jurassic period. The Jurassic period begins at 201 million years ago and ends at 145 million years ago. For our next exercise, we will calculate the rate of motion of the Pacific plate based upon the distances and ages between different Hawaiian Islands and Emperor seamounts. As a review, volcanic hotspot is an area in the mantle from which heat rises as a thermal plume from deep in the earth. High heat and lower pressure at the base of the lithosphere, the tectonic plate, facilitates melting of the rock. This melt, called magma, rises through cracks and erupts to form volcanoes. As the tectonic plate moves over the stationary hotspot, the volcanoes are rafted away and new ones form in their place. This results in a chain of volcanoes such as the Hawaiian Islands and the Emperor Seamount chain. Let's watch a video that reviews these basic concepts of hotspot volcanism. This is a video from IRIS, the Incorporated Research Institutions for Seismology, which is a consortium of research and educational institutions funded by the National Science Foundation.
A hotspot is a localized source of high heat energy that sustains volcanism. It is not an isolated shallow magma reservoir beneath the crust, nor is it a pipe of magma that streams from the outer core. One theory holds that hotspots may begin as a blowtorch-like thermal perturbation in a zone between the liquid outer core and overlying mantle about 2,900 kilometers deep. The thermal plume allows solid, yet mobile mantle to rise very slowly and convect outward. Convection is the process by which heated material rises and cooler material sinks. Although magma may be generated as deep as 1,500 kilometers, individual blocks do not traverse the entire mantle. Let's zoom in to look at the onset of hotspot volcanism beneath a moving plate. As each pocket of melt stalls, its heat is transferred to adjacent rock. This transfer continues to the base of the tectonic plate, where decreased pressure facilitates rock melting. The magma that forms at the base of this plate rises through the plate in a network of cracks and shallow chambers and erupts on the surface. Over hundreds of thousands of years, large volcanoes build on top of the plate. The weight of the volcanoes bends the plate downward. Volcanoes that spent their constructive life over the thermal plume slowly get rafted away on the moving plate, and new volcanoes build in their place. Multiple dikes can feed several volcanoes from separate conduits. The moving plate drags the thermal plume with it. This can explain why volcanoes can erupt again after centuries of quiescence, even after they have moved off the center of the hotspot. However, erosion greatly outpaces volcanism as eruptions wane, and the buoyant effect of the plume diminishes, allowing the volcano to subside.
Here is a map showing the geologic trends of the Kea and Loa Hawaiian volcanoes. This is from a U.S. Geological Survey professional paper celebrating the 75th anniversary of the Hawaiian Volcano Observatory from 1987. Here is a link to this paper. This is the map we will be using for our plate motion calculations. We will be making distance measurements between the island and seamounts that have radiometric ages associated with them. Each island or seamount that has a radiometric age is labeled with a tick mark and a number that matches the age of that location in millions of years, or MA. This is the first measurement you will make between the ends of the tick marks labeled less than 2 and 10 MA. This measurement will be your map distance measurement in millimeters. You will need to convert this to a real-world distance. Then you will divide this distance by the time span to calculate the rate of motion for this time span. This is the second measurement you will make. This is the third measurement you will make. Note how I'm measuring the distance between the ends of the tick marks. This slide gives you a hint about where to make a measurement so you can make a map scale correction ratio. This is the same thing you did in the first part of this activity. Note, this is 10 degrees in real-world distance. In this example, I measure 18.5 millimeters. From this, I can say that the map distance of 18.5 millimeters is equal to 10 degrees of latitude in real-world distance. Now all I need to do is formulate the ratio to use for each of my measurements. Your measurement may be different or may be the same as my measurement. Finally, sediment thickness can be considered a distance, so we can use this rearranged formula to determine the thickness of sediment given a sedimentation rate and an amount of time. So step 1, we will rearrange the formula to solve for distance. Multiply both sides by time, then cancel these. We finally find that distance is equal to times rate. Here are the calculations for the first determination of sediment thickness. The age of the island is 10 MA, so this is the time we will use to calculate the thickness of sediment. Use the age of each island or seamount for each of your sediment thickness calculations. For example, for the second calculation, use 20 MA. Distance is 10 MA, which is the time, times the rate, which is 2 millimeters per 1,000 years. Then we multiply this by 1 million years per 1 million years, and then we cancel MA, and we cancel years, and then we can cancel 3 zeros on the numerator and the denominator, and then multiply this out. 10 times 2 times 1,000 equals 20,000 millimeters. So in 10 million years, there are 20,000 millimeters of sediment. We can convert this to meters by multiplying 20,000 millimeters by our conversion factor of 1 meter per 1,000 millimeters. We can cancel millimeters, and we can cancel 3 zeros in our numerator and 3 zeros in our denominator to find that in 10 million years we get 20 meters of sediment accumulating. The relative fraction scale of a map is usually expressed as a ratio, such as 1 to 24,000. This is interpreted to mean that 1 centimeter measured on the map represents 24,000 centimeters in the real world. This is why the RF scale is sometimes called the representative fraction scale. One may take the map distance to the real-world distance ratio to determine the RF fraction scale. First, we need to make the units in the numerator and the denominator cancel out. Then we need to solve the ratio so that there is a 1 in the numerator. Here is an example where we begin with our map distance to real-world distance ratio as 20 millimeters to 10 degrees. We then use some conversion factors to get the units in the numerator and the denominator to cancel out. Recall that 10 degrees of latitude is equal to 600 nautical miles. 1 nautical mile is equal to 1.852 kilometers, and 1 kilometer is equal to 1 million millimeters. We can then cancel the units millimeters, degrees, nautical miles, and kilometers so that there are no units. We then divide the numerator and the denominator by the value of the numerator, and this makes the numerator 1. The result is the relative fraction scale of 1 over 55,560,000, which we simply rewrite as a ratio 1 to 55,560,000. This means that 1 centimeter on the map is 55,560,000 centimeters in the real world. Now do this for the Hawaii Island chain and Emperor Seamount chain map.